Is Renling Jin from Charleston, who speaks on hyper integers and a simple proof of Szemeredi's theorem. Please.
Okay, thanks, Mel. This work is start from a conference in 2017 in San Jose, California. In that conference, Terence Tao gave a series talk about Szemeredi's original idea of the Szemeredi theorem. And he tried to see whether non-standard analysis is a good tool to simplify the proof. And he mentioned that it's very hard. And later, after the conference, he put this statement saying that there are some signs that perhaps non-standard analysis is not the optimal framework in which to place this argument. And my work is just trying to show his statement is philosophical, but not mathematical. Okay, the simplification occurs here. In Szemeredi's original proof, he used the induction proof. The key step is induction on sets instead of numbers. Okay, so in Tao's notes, he have this theorem, which is the key induction step. There is a typo. I think it's a typo here. Oh, sorry for spreading confusion then. Okay, this K0 should be K0 plus 1. So in this induction, for example, if we want to prove Roth's theorem, the combinatorial statement to C should take like this step. 3 and empty set go to 3 and the set with one element 1 implies 3 get element 2 implies 3 get element 1, 2, but not 3. After you get all the number from 2 and below, then you jump into 3. So this kind of induction proof takes like 2 to the k minus 1 steps to complete. And this induction often make the proof less transparent. So my work is using non-standard analysis is trying to get around this induction and give a direct induction, a straightforward induction step. Okay, so Szemeredi theorems, I use a notation called KAP, which means K-term arithmetical progression. In the proof, the Tao's notes have a concept called limit along arithmetic progression, or a density along the arithmetic progression. So this is, I call it strong upper Banach density of X. Suppose you have a set X, you take AP of n terms, then intersect X and divided by the size of the P, then you let n approach to infinity, and that's exactly the concept similar, the parallel to the density along the AP. Of course, if Szemeredi theorem is true, then this strong upper Banach density of X is 1 if X have a positive density. but we don't know, before we prove it, we don't know whether Szemeredi theorem is true. Pretend we don't know. Okay, now by using non-standard setting, we have a simpler statement for the Szemeredi theorems. The bridge is like the following. Suppose we have a hyperfinite set, that means which have a cardinality non-standard, and have a positive standard real numbers, then strong upper Banach density of X bigger than equals alpha if and only if there is an AP of hyperfinite length such that the measure of X inside P is bigger than equals alpha. So we translate density into the measure. Now, what is this measure? This measure is like normalized counting measure and standardized. Okay, so what we now want to prove is if we have a hyperfinite set with positive strong upper Banach density, then this X contains K term arithmetic progression. And we use the following notation: bracket N is a set. And we use a PQR for the AP of length K, the always length, fixed length K. P parentheses I means I's term of P. And capital P is always AP of hyperfinite length. The proof using a mixing lemma, the non-standard version of mixing lemma is the following. If we have a set with positive strong upper Banach density, and we pick another hyperfinite integer h, which is less than third of the n. And if we have AP inside n, if the H contains many set of positive measure, then we can lift those sets to a certain level, so it becomes independent of X. That means the measure of X intersect this set is the alpha, which is the measure of X inside this small piece, times the measure of EW. So here's the picture. We have N, and we pick a H, which is not too large, and we put it in the vertical expression. If this H contains many sets EW, then there is a X0 inside this AP such that the X part inside this piece is independent of EW, independent of EW lifted to that level. For almost all W simultaneously. Okay, this is called the mixing lemma. Now, using this mixing lemma, we can prove the Roth theorems very easily. Suppose we have hyperfinite integer n, we pick h to be the 1/4 of this n. Then for every W inside this set H, we form a set of AP of 3 terms so that first coordinate belongs to X, third coordinate equals W. So what about second coordinates? Well, second coordinates create a set when we move the first coordinate inside X. Okay, now this set EW inside this H should have a measure alpha over 2, because in this case, the difference between the Q1 and Q3 must be multiple of 2. Okay, now we pick AP of hyperfinite length, just h to the 2h. Then we using a mixing lemma to lift those set EW into a certain level at x0 so that it becomes independent, the mixed. Okay, so the measure of this mixing is alpha times the measure of EW, which is alpha squared over 2. Okay, then we create another fixed 3-term AP, 0, x0, and 2x0. Here, x0 is this created inside by using the mixing lemma. So then we lift the W. We have lots of elements for 3rd term AP, lift to the 2x level, then the intersection must be alpha. The reason is because x is very uniform, because it realized the strong upper Banach density. So the intersection will be alpha. Now we pick one element inside the set, then we use pick one element, which is 3rd term of 1 AP. Then we use the mixing to pick a 2nd element in AP. Then we use a 1st element to belong to X already. So we create a 3-term AP inside X. So here's the picture to visualize the proof. We have N, then we pick H is like a 1/4 of the N. Then we put it upward. We create, for each W, we create a set EW, which contains 2nd element. And the 1st element is inside X. Then we pick one element in these intervals by the mixing lemma to mix this EW simultaneous for many Ws inside this piece. Then we have almost all W move to this place. Then this set intersect X have a non-empty intersection. So we pick one of them. Then using, because of mixing lemma, we have another element is in P2, and the 1st element P1 must be inside X. So we have one element in X, another element in X, another element in X, then Roth axiom is proven. Now, how can we generalize this into the proof of K equals 4? Well, first, we want to pick H less than 1/5 of the N. Then we, instead of consider 3-term AP, we consider 4 terms AP with one coordinate free. So this coordinate could be the 3rd coordinate or 4th coordinate. Okay, so we can, using exactly the same idea for the 4 APs, if we required only the first 3 elements in X, or first 2 elements and the 4th element of the AP inside X. And also we are now using 1/5 of N to be an H. And we use the same idea to prove the case for X equals 4. But in this time, we want N to be in the hyper integer. So this is like infinitely large into the previously infinitely large integers. Okay, then we have, suppose X have a strong upper Banach density equals alpha to be positive. Okay, And then we pick H to be in the first level infinity. So this H is infinitely large, but it is infinitely small than the N. Okay, now imagine, let's think about H to be as if it is finite with respect to H. Then we can find a set B such that a type of X inside this interval H plus X plus capital H are the same for all those X belong to B. For all those belong to B, you have the same type. Okay. Now, this B have measure 0 in the standard sense, but it have a positive density if we view the first level universe to be first infinity to be the standard. Then using this property, using the obviously this B have a cardinality n divided by 2 to the H plus 1. But because H is now as if it's a finite compared with N, therefore this cardinality is have some kind of a positive proportion. So, and also the we fix a type. So fix a type for every element in the B. Okay, using the case of k equals 3, we can find one version of the Roth theorems to get a collection of 4 APs such that the last coordinate is free. So it's like, sorry. Okay, the third coordinate is kind of like a W there. So have a measure 1 inside sub-intervals. Okay, and we want first 2 coordinates belong to B. So in this case, these first 2 elements will be the same type, have the same type. The third coordinate equals T. Now, how many of those R's? Well, there are many of those R's, but I only need 1. I pick 1 for each individual T. So this is an application of last case for the horizontal direction. Then we can have same idea to apply the Roth theorems with 4 APs. In this case, we leave third coordinate free. Okay, third coordinate free. Then we have T2, it's like a W there, have a measure 1 in some subintervals. So we have lots of those APs with cardinality alpha squared divided by 3. Originally it's divided by 2, but because we need a 4 AP, so we should be divided by 3. So in this case, if I leave the third coordinate free, the third coordinate will create a set of positive density. Okay, then we can using mixed lemma again to mix them into at a certain level. In this case, then we use exactly the same idea to lift the all those T2 into the level of RT4 to get some element. Then we get a free get 4 APs by using mixing lemma and the whole the sequence of Q. the AP, 4 APQs. It's I understand it's complicated, but let me just using the picture to explain. Okay, horizontally, I have a set B with positive measure in the star sense. Then we use Roth theorem's proof to create lots of 4 APs for each of the T0s. Okay, but we only need one for each T0s. Those T0s form a measure 1. Therefore, I can have hyperfinite consecutive of those P's as the arithmetic progression. And the first 2 elements belong to B, and the 4th element is free, but I just need one so that the X inside this piece have a measure alpha. Then I use Roth theorem's proof again on the H side. So I need Q4 equals W for W to have a measure 1 there in some space, some intervals. Then Q3 form a set of positive measure, and Q2, Q1 belong to the same type, tau. Then when I lift using mixing lemma, lift those EW into the level, 1 level at some T0 in the P, I mix them with X, okay? So then because the measure of those W's together have a positive measure, have a measure 1 inside some interval, then we lift into this level, we can get an intersection with X, then I get a P4. This P4, then a P3 will just picking from this mixing, and a P2, P1 belong to X because they have the same type. So Q1 belong to X here, then belong to X here, belong to X here. Q2 belong to X here, belong to X here, belong to X here. So now we have AP of length 4. Okay, all of those coordinates belong to X. Okay, now imagine how this can be extended into K equals 5 and above. Well, it becomes a little bit hard because remember, in this case, this H have a 0 measure compared with N. So we don't have measure, the measure 0 case for the mixing lemma. So the mixing lemma no longer can apply directly, but we can modify this by using something called countable saturation, and also using something like elementary extension to get around this difficulty. So the following lemma is just the lemma the key lemma for the induction. So you have this part and this part. Then the Szemeredi theorem just follows. The proof is simple induction on this lemma and carry out in non-standard universe with 3 levels of hyperfinite integers. Well, because it's time is up, I have my preprint already uploaded to archive. So anyone interested in can read my preprint.
Thank you, Renling.
Thank you.
Hey, any logicians out there? Any comments on our speaker's talk?
Well, Renling, I noticed in that page you showed from Tao's discussion of the AIM conference, he listed people in the room, and I was sitting there between Tao and Tausner, who I think I saw Henry Tausner here in the list of people.
I am
here. Yeah.
Oh,
and
yeah.
I noticed that I seem to be the one name omitted. So I obviously made a big impact in that working group. Yeah.
Interesting conference.
Yeah.
I will never understand Szemeredi's idea without Tao's lecture.
Yeah, well, I feel a little bit that Tao is like moving through a dense jungle very easily without disturbing any of the plants, which, you know, as if any other person would be moving along a superhighway. You're there behind him, sort of cutting through the jungle with a scythe. And I feel like trying to work through your paper, I'm sort of behind, trying, you know, not to fall too much out of the little path that you've created with your scythe.
Yeah, I think Tao is interesting in non-standard analysis, but probably it's not very deep. He viewed the non-standard analysis as an efficient tool to manage epsilon delta. So that's the level he has. So some tool is not available to him.
Well, you know, I'm still really curious about the iterated embedding that you're using, and
Yes.
you know, as I say, I've spent a little bit of time with your preprint, but with your paper, but for me, it's sort of slow going because it's just keeping it all straight in my head. But you know, there's always this question of whether you really need it, whether you can somehow use some kind of reflection principle to move things back and forth by moving in and out of just a single non-standard universe. But it's the use is interesting. I mean, the idea that then you can sort of move to the higher level and then look back at the middle level, where from the outside everything still looks very infinite, but from the standpoint of the highest level, it looks very, you know, very finite. I mean, it feels like it should be extremely useful. I mean,
I hope so. The people in set theory often use iterated ultra power to get some large coordinates. They use only one type of elementary extension. It's called internal ultra power, repeated internal ultra power. They never use the external ultra power, as I know. So I think there might be some room there to get something. I don't know.
Any other questions or comments on our speaker's talk? If not, then I thank Renling again for a very impressive presentation.
Thank you.
Wish you well. There's a lot to learn. And we now have a break for lunch.